guys, welcome to this video. I will be going over the June 2022 paper for AS, which is the Depth in Physics paper, and I've already done a two-part video on paper 1 of June 2022, so check it out. I'll put a link at the end of the video. So let's get right into it. So the first question is saying that a student investigates the motion of a steel ball in oil in a lab. The radius R of the ball is 8 millimeters. Okay, describe how the student can determine R accurately in the lab. So for this, we can use either a micrometer or a vernier caliper. So I'm gonna write that down. Let's put that here. So a micrometer or a vernier caliper can be used, and you have to then take repeated readings from different points. Repeat readings from different points, followed by taking an average of, let's say, 3 values. Okay, take average, and the radius is equal to average divided by 2. So 3 marks and 3 bullet points will suffice here. And for part B, we are given that the student uses a measuring cylinder and a digital balance to measure the density of the oil. The student records the following measurements. We've been given the mass of the empty measuring cylinder, the volume of the oil that's been added, and the total mass of the cylinder and the oil. So therefore, if we have to work out the density of the oil, we just need to use the formula rho equals mass over volume, and we know that the mass of the oil is the difference between these two values. Okay, so that is going to be 73 grams, or 0.073 kilograms, divided by the volume in meters cube. Okay, so 87 times by 10 to the minus 6 meters cube, and that gives me a result of 839 or 840 kilograms per meters cube, to two significant figures. So for part C now, it says that the steel ball is submerged in the oil. Show that the upthrust acting on the steel ball is this much. Okay, so we know that the upthrust acting on the steel ball is equal to the weight of the fluid displaced, of the oil displaced. Okay, and we can simply work out the weight of the oil displaced by working out force using the fluid pressure. We know that pressure in general is equal to force divided by area, the cross-sectional area, and we know that force therefore is equal to pressure times by the area, and the pressure over here is rho GH, as that it's a fluid. Okay, so therefore the upthrust can be calculated by using the fluid pressure as rho GH times by the area, and because we are neither given the height nor the area, I can simply combine these two to put it as volume. Okay, so volume, and because it's a steel ball, it's assumed to be spherical, and it is given to you by 4/3 pi r cubed. Okay, 4/3 pi r cubed. So if I put everything now in the correct units into my formula, I would end up getting, so rho is 840 times by g 9.81 times by 4/3 pi r cubed. Now r is already given to us as 8.1 millimeters. So convert this into meters cube, and as in meters, okay, so 10 to the minus 3, and then cube that. So when you combine all these numbers together, you would end up getting an answer of 1.8 times 10 to the minus 2 newtons, and that's what we needed. So that's part C done now. Right, so with question number D, it says that the student fills up a long tube with the oil, and the student drops the steel ball from rest at the surface at time t equals 0. The displacement S of the ball is measured from the surface, okie doke, and then the student has drawn this graph. That's fine. The question asks us to describe and explain how the terminal velocity of the steel ball, which is calculated as 1.8 meters per second, can be determined from the graph. Okay, so terminal velocity, we all know, is the constant velocity. Okay, so we know in general that the gradient of a displacement time graph gives you the velocity. So I would work out the gradient, okay, but it needs to be constant because the terminal velocity is constant. So the gradient of the part which is straight should be worked out. So the part that's a straight line is stretching from approximately 0.3 seconds, okay, to 0.7 seconds. So I would work out the gradient of that particular section. So if I just go ahead and read the values, just bear with me. So that is 0.3, 0.28, and that will be 0.9, 0.98. Okay, so now the gradient is going to be 0.98 minus 0.28 over the time taken, which is 0.7 minus 0.3. And that gives me a value of 1.75. Cool. Okay, so 1.75 meters per second, which can be approximated to 1.8. Okay, so I'm going to write down my answer now, and I shall say that the value of the gradient gives the velocity, but since its terminal velocity, it needs to be constant. And for that, I need the gradient of the straight line section. And that is worked out to be this value over here. So I'll put it down as a proof that I have calculated it to be approximately 1.8 meters per second to 2 sig figs. Okay, right, let's move on to our next part. So it says use a graph to calculate the velocity u of steel ball at t equals 0.2 seconds. Okay, again, we're gonna have to use the gradient. So 0.2, I'm gonna just do it in a different color. So 0.2 is right here. So I'm gonna draw a gradient at that point. So let's do that. It's not gonna be the best line, but hopefully, oops, that disappeared. Hopefully it will do. Alright, cool. So I am gonna do a full stretch. There we go. Okay. So I am getting a value along the y-axis as somewhere in between 0.78 to 0.8. So I'll take 0.78 actually, and then that is 0. Okay, so that's fine, and the time is from this particular value, which is 0.0. Okay, cool. So let's put this down, and I end up getting 0.78 minus 0 over, so this is my u value, and that's 0.7 minus 0.09. Okay, so once I pop that in the calculator, I will end up getting a value of 0.0. Okay, I get 1.278. Okay, so I can round that to 1.27. So I would say 1.3 meters per second is my answer there. So there would be an acceptable range, and I think from the mark scheme, what they accept is anything between 1.10 to 1.30 meters per second. Okay, so there we go. Right, so next part. Okay, so we've been given the mass of the steel ball as 17 grams, and the drag force F acting on the steel ball is given to us by this equation, where this symbol is eta, and it's also known as the viscosity of the fluid, and r is the radius, v is the speed of the steel ball through the oil. And at v equals 1.8 meters per second, the force is equal to the difference between the weight of the steel ball and the upthrust acting on the steel ball. So for this, we just have to work out this symbol eta, okay, so I'll just write that down over here, so eta, okay, and it's the viscosity, as I said earlier. So force is equal to the weight minus the upthrust. So weight of the ball is 0.017 in kilograms times by 9.81 times, minus the upthrust, which we calculated in our previous question in our very well part C, which is 1.8 times 10 to the minus 2. So let's put that here, which is 1.8 times 10 to the minus 2, and that gives me a value of 0.14877 newtons. So therefore, if I just rearrange for eta, is equal to F over 6 pi RV, that is going to be 0.14877 over 6 pi times by r, which is 8.1 times 10 to the minus 3 meters, times by the velocity, which is given to us as 1.8 meters per second. And that results in a value of 0.54. Okay, and in terms of the units, we can work that out using this equation. We know that force is in newtons, and 6 pi doesn't have any units, r is in meters, and velocity is also in meters per second. And so if I just write down newtons as kilograms meters per second squared, as it's F equals ma, and that becomes m squared s minus 1, that ends up tidying out as kilograms per meter per second. Okay, so that is your answer. Let's move on to the next question now. For question number 2, it says that a student is investigating the motion of a trolley as it accelerates from rest along a horizontal surface. The diagram shows the trolley on a horizontal surface, and a load of weight W accelerates the trolley. And point P is a distance D away from the initial position, okay, of the trolley, and a light gate connected to a timer is used to determine the velocity v of the trolley at point P. It is suggested that the relationship between v and the mass m of the trolley is like so, where q and r are constants, and we need to describe with the aid of a suitable diagram how an experiment can be safely conducted to test this relationship between v and m, and how the data can be analyzed to determine the values of q and r. So, to test this relationship between v and m, we would have to get a graph ultimately, and that graph, I would say, should be between 1 over v squared on the y-axis versus m on the x-axis. Okay, so in order to do that, I need to change the mass and therefore get a value, a corresponding value for of the velocity of the trolley. And to do that, I would have to do a couple of things to my diagram. Number 1, I need to place a light gate at position P. So just gonna really, it's not the best diagram, but I'll just label it clearly that that is my light gate. And the light gate is needed to measure the velocity, right? So it is going to do that by checking the length of, or rather the thickness of the card that is to be placed in front of the trolley, say here, okay? And the card is of fixed length, okay? So card of fixed length, and the light gate, as well as the trolley passes through the light gate, it would cut the beam, okay? The card will cut the beam, and therefore it is needed for that reason. Now, the other thing we need for safety is perhaps a sand bag at the end, okay, so that it doesn't fall down or you hurt yourself, so sandbag for cushioning. And now, starting off with the main thing, I'm going to split this up into 3 sections: the measurements that need to be taken, the actual method, and the analysis of the results. Okay, so as we know that it should be a straight line passing through the origin, and maybe not passing through the origin, because technically if I compare it with y equals mx plus c, the y-intercept is going to be r. Okay, so it would help me from the graph if I could read the value of the y-intercept. Okay, so let's do the first bit, which is the measurements. Okay, so measurement, the first one that you have to do is measure the length of the card using a ruler. You'd also need to measure the distance, so measure the distance d. okay, using a ruler again. Third measurement you're going to have to take is the mass of the trolley. Okay, so mass of the trolley can be altered by altering the amount of the weight that you put over here, the load that you put over here. Okay, so weight and the mass of the value of m are directly linked. So I would say measure the mass using m, using a balance weighing scale, and then you would have to calculate the value of the weight w, okay, for each mass. Okay, so those are all my measurements. Now, in terms of the actual method, let's write that down somewhere here. So the first step would be to start a stopwatch as soon as the trolley is released. So start the stopwatch as soon as the trolley is released. Now, that release can be done through an electromagnet or a clamp. You can have a clamp stand, not a clamp stand, but you can have like a clamping mechanism, like just over here, sort of, where you just let go so they can just attach over here. So that could be a clamp mechanism where you just basically, when you release the clamp, the trolley will move. Okay, so that's what I would say. And the next point will be to record the time taken, using the light gate, because the light gate is connected to a timer, as it says in the question. It says that right here. Okay, so record the time using the light gate as the trolley passes through it, as the set length of the card cuts the light beam. Okay, so light beam of the light gate. So hope that makes sense. Alright, so the next point is to actually say that using V equals the length of the card divided by the time that you've just measured, okay, you can work out the velocity, and I should say that this should be delta t, where delta t is the time taken from, or rather the difference between the time in step 1 and step 2. Okay, so that is that. It's the time recorded by the light gate, and then I can say that you need to repeat these 3 steps, perhaps 3 times, ideally 3 times, for the same mass, and then average the result out. Okay, so repeat these 3 steps 3 times to get an average velocity for a given mass, okay, of the trolley. So how are you going to change the mass? Well, you are going to alter the load. Okay, so by altering the load, i.e. increasing the weight, change, well, actually, you can change the mass of the trolley can be changed, and steps 1 to 4 can be repeated to obtain a graph of 1 over v squared versus m. Okay, so if we were, as I said earlier, if we were to compare this to the equation of a straight line, then the gradient, which is m, okay, is going to give us 1 over 2dw minus q. Okay, so I'm just going to put 1 over. Okay, so, oops, there we go. 1 over 2dw minus q. Okay, so let's put that down, because ultimately we are to work out the value of q and r. Okay, so we are down to the analysis part now. Compare the given equation to that of the straight line. Y equals mx plus c. We can say that the gradient is equal to 1 over 2dw minus q, and therefore q can be calculated as 2dw minus 1 over the gradient. And as I said earlier, the value of the y-intercept is a value of r. So, okay, y-intercept is equal to r. So that's that for question number 2. Let's move on now. Part A asks us to state the 2 conditions for an object to be in equilibrium. So the first condition is that the net force or the resultant force has to be 0. And second condition is that the sum of clockwise, okay, moments must be equal to the sum of anti-clockwise moments. Okay, so moving on to part B now. We have been given a diagram showing a uniform rod which is in equilibrium. The rod has a circular cross-section and has a length of, well, 0.6 meters, and the weight is 2.1. So it's uniform, therefore its weight will be acting through the center. And the diagram is given not to scale. The mass m is suspended at a distance of 0.1 meters from the point A, and a weight of 0.49 newtons is suspended at a distance of 0.22 meters from B. And a string is attached to the rod at a distance d from point A. The tension in the string is measured to be 3.9 newton. Show that m is about 0.13 kilograms. So first of all, I would just annotate my diagram with all the different forces given to me at various distances. So first of all, there's the mass m, okay, and the weight due to that will be mg, and that's already given to me from 0.1 meters away from A. Then what they haven't mentioned is the weight over here of the rod, which is 2.1 newtons. Okay, so if I say that that's roughly the center, then 2.1 newtons is acting at the center, and the distance is going to be 0.300 meters from each end. Okay. And we have also been given the tension, which is acting like so, and that's given to us as 3.9 newtons. So if I just took all the forces, vertical forces, okay, resolving forces vertically, will give me tension, okay, that's acting against the mg and 0.49 and 2.1. Okay, so the upward force is equal to the sum of downward forces. So as the net resultant force has to be 0. So T equals mg plus 0.49 plus 2.1, and therefore m is going to be equal to the tension, which is 3.9 newtons, minus the sum of these two, which is 2.59, over the gravity, which is 9.81. Okay, and that ends up giving me a value of 0.134 kilograms. Okay, so let's move on to the next part where, by taking moments about point A, we need to determine D. So D is the distance between A and the row. Okay, so if I took A as a pivot, then the sum of clockwise moments is equal to sum of anti-clockwise moments. So let's start off with the 3.9D that's acting, upwards. Okay, so that will be acting up and against the rest of the moments. Okay, the moments which are caused by mg, the weight of the rod, and the 0.49 newtons. Okay, so let's put them down, and I guess we just need to figure out, we have the distance from A because we are taking the pivot point as A. We have all the distances from A except for the distance between 0.49 newtons and point A. So we know that this is 0.22, and therefore this bit will be 0.08 meters, and we can just add them up together. Okay, so this distance altogether will be 0.3 plus 0.08, so 0.38 meters. So we've got all our calculations set to be done, so let's put them in here. So moment about A, so we've got the first one, which is due to mg, which is at a distance of 0.1 meters. Okay, so 0.134 times by 9.8 times by 0.1. And then we have 2.1 at a distance of 0.3, so 2.1 times 0.3 plus 0.49 at a distance of 0.38, and all that is up against the tension times by the distance from A. So quite simple calculation rather, for 3 marks. Okay, so D turns out to be, so if we put these all together, we would end up dividing it by 3.9, and that gives me 0.243 meters. So let's see whether that is actually sounding right. So 0.243 meters, well, yep, it's very likely to be correct because it has to be less than 0.3 meters. And so that's part II done for you. Let's move on to our next question now. So here we have a ball of mass 0.16 kilograms, and it's dropped from rest from a height of 2.5 meters above the ground. And assuming that there is negligible air resistance, calculate the change in GPE, or gravitational potential energy. So that is quite simply mgh. Okay, so change in EP is mgh 0.16 times 9.81 times by 2.5 meters, and that gives me 3.9 joules to 2 significant figures. Okay. Part II. What is the velocity v of the ball as it reaches the ground? So, given that energy is conserved over here, that there is no heat loss, okay, as there is no air resistance, then we can safely say that all the kinetic energy, all the gravitational potential energy lost, okay, is gained into kinetic energy. Okay, so if I just do that, so EP lost is equal to KE gained, okay, and mgh equals half mv squared, and therefore v is square root of 2gh, which is independent of the mass, basically. So 9.81 times by 2.5 square rooted will give me an answer of 7.0 meters per second. So let's have a look at the next part now. We're given that the ball from A is now fired horizontally with a speed of 12 meters per second from a bank. The height of the bank is 2.5 meters. The time for the ball to travel from the edge of the bank to the horizontal ground is 0.71 seconds. The path of the ball is shown in the diagram. The ball hits the horizontal ground at a distance r from the bottom of the bank. Assume air resistance is negligible. We need to calculate the value of r. Okay, so r is based on the horizontal speed. Okay, horizontal speed, which is 12 meters per second. So the time taken is also given to us as 0.71. So r can be calculated as u times t, or 12 times 0.71, which gives me 8.52 meters per second, and that's that. Meters, sorry. And then for the next part, we have been given that, well, we need to calculate the kinetic energy of the ball as it reaches the ground. Now, the kinetic energy is based on the speed. Okay, so this is quite a cheeky question, because if I was to just use the initial velocity, the horizontal velocity of 12 meters per second, I would get an entirely incorrect answer. So half mv squared, where v over here is a speed, it's a magnitude, okay, of the horizontal and the vertical components of the velocity. Okay, so the speed is equal to the square root of the horizontal velocity, which is 12 meters per second, okay, and we just figured out the vertical velocity of 7 meters per second in the previous part. So I'm going to work out the square root of that, so 12 squared plus 7 squared, and that ends up giving me approximately 13.9. Okay, so now I'm going to pop that in, so I would end up getting an answer of 15.4 joules. So be careful that the speed considers the Pythagoras of the horizontal and the vertical components of the velocity, especially in a projectile motion such as this. So this is a horizontal projectile, however, you know, the ball was falling down, and therefore it will have a vertical component as well, which we calculated here. So let's move on to the next part now. We have to calculate the angle between the ground and the direction of the ball as it reaches the ground. So we can say that, for example, it is this angle theta that we are trying to work out, okay, and as it reaches the ground, it will have a horizontal and a vertical component. Okay, I'm going to call this as Vx and Vy. Now, because there is no air resistance, Vx is just going to be 12, okay, and what is Vy? Well, that's just 7 meters per second. So I'm going to work that out, over here. So Vx is basically u, which is 12, and Vy is 7. So I can use tan theta as 7 over 12, and therefore theta is tan inverse of 7 over 12. Okay, and that ends up giving me a value of 30 degrees. Cool. Let's move on to our next question. Question number 5 gives us a table which shows the refractive index of air, glass, and oil for red light. Okay. It also shows the speed v of the red light in air, and we need to complete the table by determining the missing values for v, for glass and oil. Write down answers to 3 significant figures. So that's pretty straightforward. If you want to work out the speed of light v in a particular medium, we just need to know this formula, which is given to us as n equals c times v, where c is the speed of light in air and v is what we're calculating in the medium. So I can say that v is simply c divided by n. So if I just pop that in to my calculator, I'm going to end up getting 1.97 times 10 to the 8. Okay, c, remember, is speed of light, okay, which is that value, and refractive index is 1.52. So I divide one by the other. And so for the next part, similarly, I end up getting 2.05 times 10 to the power of 8 meters per second. Okay, done. Part B. Show that the critical angle for a ray of red light at the boundary between glass and air is less than 45 degrees. Okay, another formula which is given to us. So critical angle, or sine c, is equal to, just be careful, I'm denoting this by capital C, this is not the speed of light, is 1 over the refractive index of the glass. Okay, so 1 is just the refractive index of air. Okay, so I'm just going to write it down quite clearly. So n of air versus n of glass. And then I could simply do sine inverse of 1 over 1.52. And that gives me a value of 41 degrees, which is less than 45 degrees. So there we have it. Next part. Question number C says, figure 5.1 shows a glass block inside a beaker, like so. The path of a ray of red light is shown entering the glass block. Complete figure 5.1 to show the path of the ray through the block until it leaves the block. Okay, that's an easy one. So it's going to be reflected inwards like so. Okay, we'll just follow this path, and then it will just go out like So if this is straight, it needs to be just parallel to the first one, so it will be like that. Okay, now the next question. So this is part C, if I was to label it. Next part of the question says, oil is now added to the beaker as shown in figure 5.2, and the path of a ray of red light is shown entering the glass block. Calculate the critical angle C for a ray of red light at the boundary between the glass and the oil. So now, all we have to be aware of is that N1 sine I is equal to N2 sine R, right? That's the law of refraction. So N1 is simply, I'm just gonna put that down, is that of the glass, okay? And if we are dealing with critical angle, okay, we are in a way dealing with the fact that it's total internal reflection, okay? So sine R is going to be sine 90, okay? So RG sine C is equal to N, I meant NG, not RG, apologies. So N of the oil times by sine 90. Okay, so that is going to be sine C equals 1.46 over 1.52, and that gives me a value of 73.8 degrees, or 74 degrees to two significant figures. Okay, next part says complete figure 5.2 to show the path of the ray through the block until it leaves the block. So that's going to be pretty straightforward again. Now for part D, it says that the oil is now added to the beaker as shown in figure 5.2. The path of a ray of red light is shown entering the glass block. Now calculate the critical angle for this red light, and that is to be between the glass and the oil. So we know the formula of critical angle, which is sine C equals N2 over N1, where N2 is the refractive index of medium 2, which is the oil, and that is 1.46, divided by N1, which is the refractive index of the glass block, which is 1.52. And we can do sine inverse of this, and it will end up getting us a value of 73.8 degrees, or 74 degrees. Okay, so for the next part, we have to complete the figure 5.2 to show the path of the ray through the block until it leaves the block. So we know that this angle, the ray is going out from the glass into the oil as refraction happens, and because the refractive index of oil is less than the refractive index of glass, it would refract away, or it would bend away from the normal. So if I start by drawing a normal as accurately as possible, which is sort of, well, it'll do. It's meant to be perpendicular, and in an exam, of course, I would do it as precisely as possible, as accurately as possible, and I would just draw the refracted ray going away from the normal as it speeds up. So that is part II done. So for the next question, number 6, a student is investigating electron diffraction, and a beam of electrons is directed towards a thin slice of graphite in an evacuated tube. The electrons are accelerated by a potential difference of 1800 volts, and the diagram shows the pattern which is formed on the fluorescent screen on the tube. Explain why this pattern is formed. So the electron diffraction, or diffraction itself, is a phenomena that supports wave-like nature of light. Okay, and electrons also behave like waves. Okay, so that's my first point, that the electrons exhibit wave-like properties. And we know that the wavelength of the electrons, which is the de Broglie's wavelength, okay, lambda of electrons, which is de Broglie's wavelength, is roughly, it must be roughly equal to the gaps between the graphite atoms. Okay, and that is for diffraction to be maximum. Okay, when the wavelength of the light, or in this case electrons, is approximately the same as the gap between the slits, or in this case graphite atoms, it would diffract the most. Okay, so the electrons diffract. And finally, I would say about the dark and bright fringes which are formed. The dark and bright fringes and bright fringe pattern are formed due to the constructive, or rather destructive and constructive interference respectively. And that happens as electrons interfere with one another as they pass through the irregularly shaped or irregular pattern of the graphite atoms. So, respectively. So those are my 3 bullet points for 3 marks. For part B, we are given that the relationship between de Broglie's wavelength and the accelerating potential difference is like so, where m is the mass of the electron and e is the elementary charge, and we need to work out the momentum of an electron. So we know that lambda is given to us as h over p, where p is the momentum. So if we compare these two equations, we can safely say that p is the square root of 2mev, where v is the voltage, accelerating voltage, okay? So we can pop in all the numbers because we know that the mass of electrons from our data booklet is 9.11 times 10 to the minus 31 kilos. Electron charge is this, and the voltage is given to us as 1800 volts, and that ends up giving me an answer of 2.3 times 10 to the minus 23 kilograms meters per second. So let's go ahead and look at question number 7 now. We've been given an electric cooker has 2 independent heating rings A and B, as shown, and the cooker rings A and B are connected in parallel to a 230 volts power supply. Alright, so this is like mains electricity now that we're dealing with. At maximum power, ring A has a power of 1100 watts and ring B has power of 1700 watts, and show that the maximum current in the cooker is less than 13 amps. So we know that power is equal to I times V, and the total power is simply added, so 1100 plus 1700, so I'm just going to write it down, okay, divided by the voltage, which is 230 volts, so 2800 over 230 gives me 12.2 amps of current, which is less than 13 amps. Okay, so for the next part, we are given that the cost of 1 kilowatt hour of energy is 18p. Calculate the cost of using the cooker at maximum power for 30 minutes. So that is half an hour. And we know that energy is equal to power times time, and the power is 2800 watts, but this has to be in kilowatts. So I'm going to divide this by 8000 and times it by the time in hours, which is 0.5. So this will give me an answer of 1.4 kilowatt hour. So 1.4 kilowatt hours are used, and 1 kilowatt hour costs 18p. So therefore, the total cost is going to be 1.4 times by 18p, which is in pence 25.2. Okay, so for part B now, we are given that the filament in ring A is a metallic wire of length 11.8 meters. At maximum power, the wire has a resistance of 31 ohms, and the metal has resistivity of 4.8 times 10 to the minus 7 ohm meter. Calculate the diameter of the wire. This is one of the easiest questions. So let's rearrange our equation that links resistance and resistivity. So we have been given that, okay, and because we are working out the diameter, which relates the area, I'm just gonna first of all put down R as rho L over pi d squared over 4, okay, because it's R squared, so R is d over 2, so it becomes squared, and if I just rearrange everything, then d square rooted, well, equal to the square root of 4 times rho L over R pi, okay, so skipping a few steps, okay, but that's quite basic. So I'm going to pop in all the values now because I know resistivity is 4.8 times 10 to the minus 7, length is 11.8, resistance is 31 times by pi, and that gives me the diameter of 4.8 times 10 to the minus 4 meters. So for the next question now, part C, we have to show that, well, we've been given a circuit symbol for ring A, and a student uses a battery of 4 cells, an ammeter, a voltmeter, to determine the resistance of the wire in ring A experimentally. Complete figure 7.2 to show how the student should connect the circuit to determine the resistance. So I'm just gonna do it over here. So we need a battery of 4 cells. Let's start with that. So we have 1, 2, 3, and 4. And I'm gonna use a variable resistor so that I can change the current through, and an ammeter, and of course the ring A, which has a circuit symbol like that of a resistor, and a voltmeter placed in parallel to this, like so. So that is the variable resistor could be optional because it doesn't quite say in the question itself that the student is using this, so I'm gonna just leave it there, but put that's option. Okay, so without the variable resistor, it's also going to be fine. Okay, so for the next question now, part II, we're given that the current in the wire is 0.34 plus or minus 0.02 amps, and the voltage or the potential difference is 6.2 plus or minus 0.2 volts. Calculate the resistance. Okay, yet another easy question. R is equal to V over I. Okay, so 6.2 over 0.34, and that gives me 18.24 volts, ohms. Calculate the percentage uncertainty in R. So for percentage uncertainty, I need to have it in terms of, I need to work out the percentage uncertainty in I and V and then add them together. Okay, so for I, it is 0.02 over 0.34, and that would give me times by 100, so 5.88, and then for V it is 0.2 over 6.2 times by 100, which is 3.23%. You add them together, okay, and you will end up getting the percentage error in resistance, which is 9.1%. Okay, so that's part III done. Now the fourth part is asking us to suggest why R from CII is less than 31 ohms. So the value of R in II is 18, roughly 18 ohms, okay, to two significant figures, which is way less than 31 ohms. And there could be lots of errors, okay. One of the main thing is that over here we are using a circuit which is basically using batteries. Okay, now batteries are very likely to give you less current, okay, and compared to the mains. Okay, remember this was the 31 ohms of resistance was based on the fact that the cooker rings are connected to 230 volts power supply. All right, so that's going to be one of my points over here. So I'll say that batteries, or well, battery over here provides lower current, okay, than mains. And secondly, I would say that there's going to be an element of heat loss, okay, because the temperature of the wires in the circuit can increase, the heat loss will increase, and therefore the current will, well, the resistance will also be higher. However, we're talking about the resistance of the wire. Okay, so that's going to be the case. So I'm going to say that the temperature of the wires in the circuit can increase the heat loss. Okay. Next question, number 5. Suggest 2 improvements to the student's experiment to determine R experimentally. So one of the improvements is that the student could use a variable resistor, okay, so that, or a variable power supply, okay, so that it's easier for the student to alter the current passing through, okay, and therefore obtain a graph of V against I. And so using the gradient of the graph, you can measure the resistance, okay, so that's what I would suggest. So use a variable resistor slash variable supply, and plot a graph of V against I to obtain a gradient. And it depends on if you're doing V against I, that's basically like so, okay, the gradient will be giving you the value of the resistance as R is equal to V over I. Okay, so doing a gradient to measure resistance R. Okay, so let's move on to our next question now. We are given that in an experiment to investigate microwaves, a microwave detector D is placed 100 centimeters from a microwave transmitter T. A thin metal sheet is placed parallel to the line joining T and D. Point R is at the bottom of the metal sheet. The perpendicular distance between this line and and point R is Y. The diagram shows the path of the microwaves traveling directly from T to D and the path of the microwaves traveling from T to reflector R, okay, to D again. So there is 180 degrees phase change when the microwaves are reflected at R, okay. Further to this, we are given that the metal sheet is moved away from the line joining T and D so that Y increases, okay. And the metal sheet remains parallel to the line from T and D, okay, that's fine too. A series of maximum and minimum intensities are observed. And here's the values of maximum and maximas and minimas, or rather maxima and minima. And we need to explain the presence of the regions of maximum and minimum intensities and determine the wavelength of microwaves. Okay, so the idea behind maximum and minimum intensities happens due to, well, superposition. So when two or more waves meet in or out of phase, they superpose. So that's my first point. So I'm gonna try and summarize this in 5 or 6 key points, okay? And I'll deal with this first, okay? So this point first and explain this. So I'd say that when two or more waves meet in phase or out, they superpose. And maximum intensities will occur when the path difference is equal to n lambda, where n is simply integer values. Okay, so from 0, 1, 2, and so on. And let's say that when y equals 8.4 centimeters, okay, when y is 8.4 centimeters, the length of TR, or just basically if you look at sort of this triangle, okay, you'll notice that the bottom or the base is fixed, okay, which is 50 centimeters. The only thing that's changing is the length. This is increasing, okay, and the starting value is 8.4. So if you work out TR, okay, just using Pythagoras, so TR is the square root of 8.4 squared plus 50 squared. I'm not going to change them into meters, okay. That gives me 50.7 centimeters, all right, and that's basically the same for RD as well. So this is 50.7 centimeters, and so is this, okay, and so that's the most important point, okay. That's your path taken from T to D, all right. So let's write that down quite clearly, all right. So when y is equal to 8.4, dr is 50.7 centimeters, which is also equal to rd. So therefore, the path taken to form first maximum at D is 101.4 centimeters. Okay, and now similarly for a minimum, okay, we know that a minimum is formed when the path difference is n plus a half lambda. Okay, so minimum occurs at path difference of n plus half lambda. So basically that's when the destructive interference happens. Okay, so that's destructive interference. Now I'm going to say that the first minimum is formed when y equals 11.9 centimeters, right? So again, for this, the value of TR is going to be, so just work this out over here, 11.9 squared plus 50 squared, and that gives me 51.4 centimeters. So again, let's write this down clearly. Okay, so first minimum occurs at when path difference, so when y equals 11.9 centimeters, the path taken results into 51.4 times by 2, which is 102.8 centimeters. Okay, so likewise for the other two maximum and minimum intensities, the path values, so I'll write that down here, so for successive maximum and minimum intensities, these values are, just going to work those out here, so what's that, so 52.1 centimeters, and then finally for this bit it is 17 squared plus 50 squared, which is gonna be 52.8 centimeters. Okay, so let's write them down. So they are 104.2 centimeters and 105.6 centimeters respectively. Okay, so let's talk about what is, so these are the paths taken. Okay, so the path difference is going to be the difference in the original path, right? That's just 100 centimeters from T to D, okay? And the path that's actually taken by the microwaves, which is from T to R and R to D. So that's the difference between. Okay, so the successive, or rather the path differences, I'm just going to write them down. Path differences of 1.4 centimeters, okay, because that's 101.4 minus 100, okay. Similarly, you have 2.8 centimeters, okay, followed by 4.2 centimeters and 5.6 centimeters. That is basically the 100 minus the values above. Okay, that's how I ended up getting it. Alright, so the path differences are done. And now for the last bit, I need to work out the wavelength. So the wavelength is basically, we can use the path difference again, okay? And in terms of the fact that it's going from maximum to minimum and again from minimum to maximum, okay, the path difference happens to be lambda over 2, okay, because I don't think I'm going to need to write that, the reasoning behind that down, but I will explain it over here. Why is that the case? Okay, so for a maximum, we know it is n lambda. For a minimum, it is n plus half lambda. Okay, so when, let's say n is equal to 1, then it is going to be lambda, and it's going to be 3/2 lambda. So what is the difference between the two? The difference is half lambda. So it will just repeat itself, okay, for the other maximum and minimum intensities. So there you have your path difference is equal to lambda/2 for maximum and minimum intensity. And therefore, if I was to use one of the values, say 1.4 centimeters, that's the first one. Okay, so lambda/2 equals 1.4. Therefore, lambda is equal to 2.8 centimeters. That's the wavelength of microwaves. So that is a really good 6 marker. I hope you understood it. And basically, that's the end of the paper. I hope you found this useful. Let me know in the comments if you have any questions or concerns. Thanks ever so much for watching.